Hi, this is week 11, lecture 2 review. And it's the last lecture. Hooray! The quiz covers week 5 through 11, but as you've seen, most things in physics build upon each other. These slides pull important points are from the following topics: rotational motion, torque, rotational energy, angular momentum, work and energy. I'm sorry, I meant rotational inertia. Thought that was odd. Um, Work and energy, power, rolling motion, and gravitation. But I'm just going to go through these slides because I think it would be better to focus on working through some examples for you. So I'm giving you these slides to review from, and instead I will work through these problems. Week 6 practice, problem 4. Week 7 practice, problem 3. Week 9, lecture 2 self-check, and week 10 practice, problem 4. Okay, so week 6 practice, problem 4, which is chapter 9, exercise 1. A particle is located at coordinates 2 meters, x equals 2 meters, and y equals 3 meters. What is the magnitude of the torque about the origin when the particle is acted upon by force of magnitude 5 newtons in A, the positive x direction, B, the positive y direction, and C, the negative x direction? So, and I have it drawn for you, and there's angles on here, but we'll talk through those because that appeared to be, if I'm remembering correctly from going through your practice assignments, that appeared to be where there were some issues. Was kind of figuring out what the angles were. So to start out, we have theta A, which is 90 degrees minus phi, which is this angle down here, phi, because this angle here is also theta A, same as that one. And then we can get phi from the x and y position of this point. So let's see, tangent, let's do it that way. Tangent of phi is going to be opposite, so x over adjacent y. And so if we take the tan inverse of both sides, phi equals the tan inverse of 2 meters divided by 3 meters, and that gives us 33.7 degrees. And this is then 56.3 degrees for theta A. And then theta B, you can see from here, actually, theta B is just equal to phi. So that's 33.7 degrees. And finally, theta C is here. And that is 180 degrees being the whole, let me just draw this here real quick. So 180 degrees is this whole thing. And then we have a 90 degrees in it between the force B and force C. And then this angle is theta B. So we're trying to find theta C, which is this angle. Hopefully that is clear enough anyway. So 180 degrees minus 90 degrees minus theta B, or 33.7 degrees, and that gives us another actually 56.3 degrees. Okay, so now that was one of the points that resulted in some difficulty in solving this problem. And then the other thing to remember too, well, is first that torque equals RF sine theta, and R is the distance from the pivot point, or this case it asks us for the torque about the origin. So we need the distance to the origin, and we're given those X and Y coordinates. And that distance will be X squared, the square root of X squared plus Y squared, which is 3.6 meters. So we can then solve for the torque in each of the situations it gave us. So the torque in A is 3.6 meters times 5 newtons sine of 56.3 degrees. And this was 15 Newton meters. And then B, 3.6 meters, 5 newtons, and sine of 33.7 degrees. And that is 10 Newton meters. And then for C, the angle is the same as A, and so is the force. So the torque is also, so it's also 15 Newton meters. Okay, so briefly, just to go over this problem again. So the thing we needed to figure out was the angles, because torque is given by RF sine of theta, where theta is the angle between R and F. Let's see. Let's draw it down here really quick so it's at least a little easier to visualize things. So we're given these three forces acting, and because we're looking at torque, we need to know the angle between the forces. So A, B, C. This means this is theta A, this is theta B, this is theta C. And this is also theta A. And we started out with calling this phi, but we did find out that that was also just theta B. But we can start by finding phi because we're given the X and Y here, and phi is this. And so that's why we did the tangent. Tangent of phi equals X over Y. Then this between A and B is 90 degrees. And we know that phi equals theta B. So A equals 90 minus phi or theta B, whichever one you want to put. And then here, this whole thing is 180 degrees. And we can use the 90-degree angle and theta B again to find theta C. Theta C equals 180 minus 90 minus phi, which is also theta A. Yeah, so hopefully that helps clear up the angles instead of confusing it more. Let's move on to the next one. So this is from the week 7 practice. It's question 3, which is from chapter 9, exercise 19. And we're asked to find the rotational inertia for 2 long thin rods of length L and mass M with 2 particles mounted to the end of them. So the way I recommend doing this one, and this is what I put in the solutions, it's to think of this as one rod with length 2L and mass 2M. And that allows you to do your total rotational inertia is equal to the inertia of the rod plus the inertia of each mass. Instead of getting all caught up in either missing some of the masses of the rods, because sometimes people like forgot about the individual rods each having a mass m. So I think this is just an easier way to do it. So that tells us that the rod is then it's rotating about an end, which is 1/3 ml squared, but in our case, that's 2m and 2l, so 2m 2l whole thing squared. So that gives us 2/3 times 4 ml squared, or 8/3 ml squared. So that is the rod. And then we'll just call this one 1 and that one 2. For mass 1, it's just ml squared, because for a particle equals mr squared, and that's just the distance from the rotation. And for mass 1, that's just L. But then for mass 2, it's 2L. That was also a spot, I think, where people were forgetting. M2L squared, which gives us 4ml squared. So when we put them all together, we get 8/3 capital ML squared plus ml squared plus 4ml squared, or 8/3 ml squared plus 5ml squared as the total rotational inertia. So I just wanted to go over this one because I think it was a lot easier than people realized. And so I just wanted to highlight that, like, you can definitely simplify these. So now this problem, so we had these objects on an inclined plane, and we wanted to know who would win a race if they were all released at the same time from rest. Like, and by winning the race, that just means gets to the bottom first. So in order to solve this, we want to use conservation of energy. So we have the initial kinetic, initial gravitational potential, final kinetic, and final gravitational potential. But these all start from rest. So this is 0 because the initial equals 0. And then they're all going to the bottom of the incline. So this is 0 because y final equals 0. But for everything except for the particle, they're rolling. We have to use this for the kinetic energy of rolling motion. So we have mgy, or h, I guess they gave us as h. So mgh is the initial gravitational potential. And then we plug in the rolling kinetic energy. So 1/2 I omega squared plus 1/2 m v squared. I guess it listed them all as having mass capital M. So maybe I'll do that just to be consistent. Okay. And then since what we want to know is the velocity at the bottom, because the one who's moving the fastest will get to the bottom first. So we want to get rid of omega, or the angular velocity, so that we're just looking at linear velocity because that's easier. And that is v over r. So let's mgh equals 1/2 I V over R squared plus 1/2 mv squared. And then we end up with this equation that we can use to solve for our different situations, or well, different objects. So we end up with mgh equals v squared over 2 times the rotational inertia divided by the radius squared plus the mass. This is only for these three. The hoop is one of those three. The particle has a separate equation that we'll get to in a second. So let's start with the hoop. And the rotational inertia of the hoop is just mr squared. So we have mgh equals v squared over 2 times mr squared over r squared plus m. Or we end up with these canceling out. So v squared over 2 times 2m, or just mv squared. And then we can solve for v, but we have capital M on both sides, so that cancels out. And then we square root, so we end up with square root of gh equals the velocity for the hoop. Next up is the cylinder. And the cylinder's rotational inertia is 1/2 mr squared. So we can plug that in. mgh equals v squared over 2 times 1/2 mr squared divided by r squared plus m. So those r squares cancel out again. And we end up with v squared over 2 times 1/2 m plus m. And that actually, this part gives us 3/2 m. So v squared over 2 times 3/2 m gives us 3/4 mv squared. And we can cancel out the mass again. And we get that the velocity, velocity equals the square root of 4/3 gh. Next up, we have the sphere, which has a rotational inertia of 2/5 mr squared. Again, we'll plug it into our equation. 2/5 mr squared over r squared plus m. So those cancel. And v squared over 2, I'm going to pull them out this time. And then it's 2/5 plus 1. That is 2/5 plus 5/5, because that's 1, gives us 7/5 for this. So we end up with 1/2 v squared m times 7/5. And when we multiply by that 1/2, we end up with 7/10. So we cancel out that m again. And the velocity is the square root of 10 divided by 7 gh. Now we will do the particle, which is a simpler relationship because we don't have to worry about rotational motion because it's a particle. So I'll write that one out. We already decided that there's no initial kinetic energy and there's no final potential energy. So mgh equals 1/2 m. That's the wrong m. V squared. So those m's cancel, and we end up with the velocity here equals the square root of 2gh. So let's just review our results. We have velocity of the hoop equals the square root of gh. Velocity of the cylinder equals square root of 4/3 gh. Velocity of the sphere equals the square root of 10/7 gh. And then finally, the velocity of the particle equals the square root of 2gh. So what we end up with is, well, let's list them like this. Like we've got, what do they call that? Podium. The end of the Olympics or something. So first place is the particle, because it doesn't have to worry about rolling. And then is the sphere, then the cylinder, and the hoop is in last place. Poor hoop, so sad. So I'll briefly just go over that again. So it started here, and part of why I wanted to show you this way too is I think it's important to practice ways of solving problems that are just more efficient too. And so by not plugging in the rotational inertia in the beginning, I was able to start from an easier point for all of them and just plug in the rotational inertia at this stage. I could have simplified it even more, gotten to a solution with velocity equals all of this stuff, but this it's just as easy. So anyway, we had our initial kinetic energy was 0, because it started from rest. We had our initial potential energy, final kinetic energy, and then our final potential energy was 0 because it went to y equals 0. We did some manipulation of those results and plugged in this for omega, or the angular velocity. And we got that equation, and then we just went through with each rotational inertia, plug them in, and solve for v for the 3 objects that are rolling. For the particle, we could just do regular conservation of energy without rolling motion. So yeah, that's this problem. Okay, now this last example is from the week 10 practice. I don't know how you all did with this one yet, because I'm recording this obviously before you have turned it in. But I thought this was a good example of energy conservation with this like gravitational potential energy. I think we're just gonna do, I think just A through C, maybe at the very least A and B. So it asks us to calculate this escape speed on Europa, which is a satellite of Jupiter. Satellite in this means moon. So just so you know, I don't think I said that in the lectures so far, but that's what that meaning is. And the radius of Europa is 1,569 kilometers. And the free fall acceleration at its surface is 1.3 meters per second squared. So for A, they asked for the escape speed. For B, they want to know how high a particle will rise if it leaves the surface of the satellite with a vertical velocity of 1.01 kilometers per second. And then we'll see if we decide to do part C. So the equation, here, we'll label this A and write the important points from that part, which was the radius and the free fall acceleration meters per second squared. And then the escape velocity, escape speed, comes from this equation, 2gm over r, square root of 2gm over r. So, but we don't know what m is. And they actually don't have you solving it until part B. So instead we will use, because we know what the free fall acceleration is and we have an equation for that, gm over r squared. And if we want it to match up with this part, we can just put r on the other side of the equation. So we end up with g naught times r equals gm over r. And we have r and g naught, so we're set there. We can plug this in, and we get that v equals the square root of 2 g naught r. Perfect. We know all of those numbers, so we can plug in 2 times 1.30 meters per second squared. No, that's a squared. Times the radius, which is 1,569 kilometers. So times 10 to the 3 to get us into meters. And this gives us a velocity of 2019.8 meters per second. But in kilometers per second, that is 2.02 kilometers per second. So then part B asks for H max if the initial velocity is 1.01 kilometers per second or 1/2 the escape velocity. And so this is where we start with energy. And this is the main reason why I wanted to do this problem, because I like tying it all together this way. So we have the kinetic energy initially, plus the gravitational potential energy initially, is equal to the gravitational, oh, sorry, I'll also put the kinetic, but that's 0 as a surprise. Plus the UG final. So this is 0 because we're assuming the max, well, we know when we're asked for maximum height in this sort of motion, it is when the velocity is 0. So, our kinetic energy is 1/2 mv squared, and then the gravitational potential is negative gmm over r. So let's plug that in. 1/2 mv squared minus gmm over r equals oh, so I'm sorry, I didn't actually fully explain this part. So we are not assuming 0 for the gravitational potential energy on the surface of the Earth. And so we're taking it into account in this situation. So it's not 0, and r here is just the radius of the Earth. But then here, gmm over the radius of the Earth plus the h max. I'm not going to put the max. It's just going to be h for this. And that's what we're trying to solve for, is that h. And let me see one. Okay, we're going to invert both sides to the -1 because we want to solve for that h, so we want to get it on top. So we end up with 1 divided by 1/2 mv squared minus GM over R. Actually, sorry. Well, rewind. Let's cancel out that M. It's in every term. Why would we keep it? Little m, goodbye. Then we will invert. 1 divided by 1/2 v squared minus G big M R. And that equals, and then we just flip this fraction over, R plus H, whole thing in parentheses, I guess, over GM. Now, we can multiply GM on both sides to get rid of it over there. Let's do negative GM, actually, so we can get rid of that negative one also. Negative GM over 1/2 v squared minus GM over R. And that gives us R plus H on this side. And then we just subtract R on both sides, or from both sides. Just put it minus R. And we end up with negative GM for 1/2 v squared minus GM over R minus R equals H. Okay, so we have solved for H, but we don't know what M is still, because again, they don't ask you to solve for it until later, so we have it. But that's fine, because these are the things we have. We have GM over R, which we already found is equal to the free fall acceleration times R. And then GM, which is just the free fall acceleration times R squared. So we can plug those into our equation. And we get, let's see, G naught R squared, negative G naught R squared over 1/2 V squared minus G naught R minus R equals H. Okay, and I think at this point we can just plug in our numbers, but of course I've run out of space. So I'm going to copy this over and we'll plug in our numbers on the next page. Okay. So negative 1.30 meters per second squared times the radius 1,569 times 10 to the 3 meters squared, or divided by 1/2 1.01 times 10 to the 3 meters per second squared minus 1.30 meters per second squared times R, which is 1,569 times 10 to the 3 meters. And then we subtract R. 569 times 10 to the 3 meters, forgot the 3. Yes. And that gives us, and this is what H equals. This gives us an H that is 5.23 times 10 to the 5 meters, or 523 kilometers. So the maximum height is 523 kilometers from the surface of Europa. And I'm sorry, when I was initially introducing this, I said radius of the Earth, but it's radius of Europa. So let's go back through these two parts, and then I'll also just talk you through part C instead of doing it, because I feel like it would be good. Well, hopefully you've already done it, but if you struggled, it would be good practice. So we have the radius and the free fall acceleration on Europa. And we wanted to know the escape velocity, which comes from this equation here. So using the equation for the free fall acceleration, we were able to solve this without having to find the mass of Europa. And we found that it was 2.02 kilometers per second. And then we were asked what the maximum height would be if the initial velocity from launch from the surface of Europa was half of that escape speed. And so we had our conservation of energy where we start with kinetic energy plus potential, and this is the potential being on the surface of Europa. And then the final, which we assume is 0, plus the final gravitational potential, which will be the surface of Europa plus the height above the surface, which is what we're solving for. This was just algebra. And then we, again, because we don't know the math, which honestly maybe would have been easier to solve for it sooner, but the point of the problem was to wait to solve for it. So we just went back to our free fall acceleration equation and rearranged things to match what we had here. Plug that in, and we got the maximum height of 523 kilometers. Let me bring you back to the question prompt itself so we can look at C, which says, with what speed will an object hit the satellite if it is dropped from a height of 1,000 kilometers? So for this too, you want to use conservation of energy. Initial kinetic energy is 0 because we're assuming dropped, meaning released from rest. The final is gonna have the final velocity that we need. And this is kind of just the reverse situation of the finding H max, where we're given the height, but we need to find the final velocity instead of the height. Just solving for something else. And you still want to do the same thing where you use the local free fall acceleration equation to avoid solving for the math, because part B asks you to solve for the math, which obviously you could just do from this equation or this equation, either one. Okay, that is the examples. Hopefully those are helpful. Yeah, thanks for a great quarter.